Thank you very much, and good morning, everybody. So my name is Davide CANALI. I'm going to present this work about the web attacks. You'll see you will see what this is about. I'm actually a PhD student at the Software and System Security Lab at Eurocom. That is a small graduate school in Côte d'Azur. I'm actually at the end of my PhD, so if any of you has interesting career opportunities for me, just send me an email or we can chat later. My main interests are web security, malware, and large-scale data analysis. And what is interesting about this work is that this work is about all of them. So what we wanted to do when we started this project was to study the internals of web attacks. And in particular, we wanted to know what attackers do while and after they exploit vulnerabilities on websites. And this would allow us to understand why attacks are carried out. So there are people who attack websites for fun, others, they just do it for profit, and others just want to damage somebody else. And we noticed before starting that the previous studies had concentrated on how attacks against websites are carried out or on how attackers find their victims on the internet, but there was a lack of studies on the actual behavior of attackers. And the reason for this was that all the previous works used, almost always used static and non-functional honeypots. So if you have a non-functional honeypot that just simulates a service, the attacker can actually send malicious payloads to that website. But of course, it wouldn't be, there's no real web service, there's no real service behind that, so the exploit won't actually happen. So we wanted to go farther. We wanted to analyze what attackers do once they're inside the machine. So this is the infrastructure we set up. We set up a total of 2,500 vulnerable web applications on a total of 500 websites that were hosted on a total of 100 domains we registered. And we installed on each of these 500 websites 5 common content management systems, among which a blog, a forum, an e-commerce web application, a generic portal such as Joomla, and a SQL manager, plus one static website along with 17 PHP web shells that allowed the attackers to log into the web shells and try to mess up with the static websites to perform, for example, a defacement or just whatever they wanted. In detail, this is the structure of the infrastructure we set up. So we had this kind of, this schematized the honeypot website we set up. We had 500 of them over the internet. And each of them was just consisting in a single HTML page that there was actually a proxy that redirected all the traffic it received to the real web applications, to the real vulnerable web applications that were actually hosted in virtual machines in our premises. So what was nice was that we just had to manage 7 virtual machines, and we had actually 500 websites pointing to them. So we had a centralized management of the system, and also this allowed us to have all the attackers reaching the websites. They weren't able to understand that they were behind a proxy, actually. They were just interacting with a normal website. They were just clicking links, and all the proxying and bad stuff was happening behind. So that was nice. That was quite transparent for the normal end user. Of course, when you set up a network of functional honeypots with real web applications behind, with real vulnerabilities, you have to address some important concerns. Because you don't want, for example, attackers to be able to run privilege escalations attacks against your machines, because otherwise, well, you're rooted and they can do whatever they want, and that's not good. So to prevent this, we did our best to have machines that were up to date with regard to software and security patches. We also exposed only one service to the internet. That was the web server. And it was actually run as an unprivileged user inside a Linux container that was running inside the virtual machine. So we're pretty safe on that side. Also, a very important thing is that when you have a honeypot, you have to avoid attackers to be able to use your honeypot as a stepping stone for other attacks. Because otherwise, the attacker could actually, once he is inside your machine, he could upload a brute forcing script or denial of service script and try to launch attacks against other machines on the internet. In this case, you would be in trouble. So to prevent this, we just blocked all outgoing traffic from our machines, and we logged it. Another very important concern is to being able to avoid attackers to host illegal content. To do so, we just prevented the modification of directories and HTML and most HTML and PHP files. So basically, we decided by means of setting permissions on files, we just decided which files to be modifiable by attackers. So we didn't want, for example, configuration files or important stuff to be modified by attackers. Also, an attacker could, for example, install a phishing website on our machines. In this case, what we would do is just we restore each virtual machine to its original state periodically, and so that we are sure that like 4 hours after any attack has taken place, the machine is actually clean again. And finally, another thing you would have to take care of if you install a web honeypot is that you want to avoid attackers to promote illegal goods or services. For example, you want to avoid them to perform spam. And this happens especially when you host a blog or a forum or applications like that that allow people to post comments or insert links into your web pages. What we did in this case is that we had a forum, we had a blog. We modified the source code of the forum and the blog, for example, to disable the code that shows the actual content of posts. So in our forum web application, for example, we allow people to post threads and post to the forum, but when you click on the title of one thread, you just see a blank page, a blank message. On the counterpart, of course, we log this in our database, so we're able to analyze what people post. So here's a short timeline of the project that spans about 1.5 years. We actually started back at the end of December 2011. That was the first part of the project. As you see in the yellow part, we ran our first experiment. We first put our honeypots up for about 100 days. During this period, we collected data, and so most of the statistics I'm going to present later are from this period, because we were able to do a very in-depth analysis of what we collected. Then we went down for some time, because of course we're an academic institution, and we couldn't afford to keep all the infrastructure online for a long period, just because it was a bit too expensive for us. Especially on the hosting and domain registration side. But fortunately, last December we were able to find a sponsor to keep our infrastructure online. So once we knew it, we started to re-implement the infrastructure. We completely redesigned the infrastructure. We improved especially the clustering and file analysis part. I will talk about this later. And we also started designing a web interface to analyze the data we collected. In February 2013, we got a paper about the first part of the project published at the NDSS 2013. So if you're interested in the details of this work, you can actually go and check the contents of the paper. And then now this month, we went back online with the new infrastructure. So I'm going to be able to show you, for example, the new web interface in the demo I'll do at the end of the talk. So I'll start talking about the first part of the project. So the data we collected and the results. We ran our experiments for a total of 100 days in 2012. As I told you, we centralized our data collection to allow us for a simple and effective management of the honeypots, because we only had to manage the 7 virtual machines. And by doing so, we collected every day, for example, the files that were created or uploaded on the honeypots by attackers, the raw logs of the web server, and database snapshots for the applications, and also the log of outgoing traffic that was blocked. This graph shows the amount of data we collected over the 100-day period. We got a total of about 10 gigabytes of raw HTTP requests. And in average, that amounted to about 1 to 10,000 uploaded files every day, and 100 to 200,000 HTTP requests every day. And what is interesting is that on the graph, we have the number of requests per day hitting our honeypots, and the blue line is actually the number of requests from known crawlers, such as Googlebot. So these are benign crawlers, and we can see that the requests from these systems is actually pretty much stable over time. While the number of requests from other systems, so for example, visitors and attackers, kept increasing almost linearly. And this is a result of the fact that as honeypots got indexed by search engines and also indexed or posted in hacking forums, people were visiting them more and more. This is another view of the requests we received by country, but this time excluding the crawlers, the benign crawlers we identified. And you can see that basically, well, the call intensity is logarithmic. So this means that IPs from USA, Russia, and Ukraine are together accounting for about 65% of the total traffic we received. So they're really the major attackers of our honeypots. And we also can see that we had a pretty much complete coverage all over the world. We received the requests from every country except for some countries in Central Africa. And okay, so going to the actual analysis of the attacks, we had a lot of data to analyze, and we had to find a decent way to show the results and to actually proceed with the analysis. So we decided to split the attack analysis phase in four different phases that relate to how attackers reach the honeypots, how they perform their scans, how they attack the application, and so on. So the first phase we identified is the so-called discovery phase that relates to how attackers find their targets on the internet. And in this phase, we analyze the referrer with which attackers reach our honeypots and the dorks they use to search for our websites on search engines. And in this phase, from the analysis of this phase, it turned out that about 70% of the attacks started with a scout bot that was visiting our pages by disguising its user agent as a known bot. For example, some people were visiting our pages by saying, I'm Googlebot, but of course they came from a DSL IP in Romania. Then second phase is what we called reconnaissance phase that relates to how pages were visited. So in this phase, we identify the automated systems visiting our honeypots, the eventual crawling patterns that were used, and we also analyze the user agent used by attackers. And actually, we found out in this phase, in 84% of the cases, the attack is launched by a second automated system that this time we call exploitation bot that often doesn't disguise its user agent. So they just leave a curl or lib/perl as a user agent. So it's clear they use a script. Third and most important phase of the attack is the exploitation phase itself. That is where the attack against the vulnerable application takes place. And in this phase, we perform an analysis of the exploits that are used. We identify exploitation sessions. We categorize the files that are uploaded to the honeypots. And we also normalize the time and location of attacks. We also analyze the forum activities we encountered, but I'll talk about this later. In this phase, it turned out that about half of the successful exploit we received uploaded a web shell on the machine. And as a result of uploading a web shell, or just a PHP file, typically that allows people to mess up manually with the application, we also identified what we call the post-exploitation phase of an attack. That happens only when the attacker has the ability to manually log in into the machine, so by using a web shell, for example. And in this phase, if it happens, we also are able to perform session identification and analysis of the comments that attackers issued to the web shells. When these kind of post-exploitation sessions happen, we realize that they happen about 3.5 hours after a successful exploit. And the typical attacker in this case reaches the uploaded shell and performs a manual attack for about 5.5 minutes. Okay, so going to the first phase of the attack, just to show a bit more details about this. As I said, the discovery phase shows us where visitors are coming from, and we see it from analyzing the referrer header of the requests we received. The referrer header is actually set in 50% of the cases, and we found out that attackers find our honeypots mostly from search engine queries, Google especially, then Yandex being Yahoo, and other specialized search engines. And we also, interestingly, receive some visits from webmail services. And this is interesting because in this case, it's not attackers, but these visitors are actually victims of spam or phishing emails, because they receive the phishing email with a link pointing to some kind of content on our honeypots. They click on them, and they get redirected to what is supposed to be the phishing page. But of course, in this case, we already cleaned in like 90%, 99% of the cases, the malicious content has been already removed by us in the meanwhile. We also received some visits from social networks. So to the reconnaissance phase, okay, as I said, we saw that 84% of the malicious traffic we received was from automated systems. And how did we find out these were automated systems? Because first, most of them don't request any image or style sheets. So of course, they are scripts, or, I mean, nowadays it's very rare for people to browse the internet using links or other text-based browsers. So we guess these are automated systems. Especially also, these systems have a very low inter-arrival time, so they perform multiple requests per second, and that cannot be a normal user. And also sometimes they visit multiple subdomains within a very short time frame. That is very typical for crawling systems. We also find out that in this case, almost 77% of the requests mimicked the user agent string of known search engines. So the exploitation phase then has been analyzed by having a look at the exploitation sessions. So we defined an exploitation session as a set of requests, of exploitation requests, that can be linked to the same origin and are arriving within 5 minutes from each other. We identified more than 400 of them, and among them, 75% of them were using at least once lib/Perl as a user agent string. That is typical for scripts that are running for Perl scripts. So these are automatic attacks. And as I said before, almost one exploitation out of 2 uploaded a web shell. As you can see, it's the blue part in the graph. Then, okay, the legend got a bit screwed up, but then you can see that there are also quite a lot of phishing files, and also a lot of irrelevant files that are typically images or other kinds of weird file or broken data that are typically uploaded during the facements. So going to the forum activity, we decided to have a look in depth at what happened on the forum web applications we set up, because we had quite a lot of traffic on this application. We actually received, in average, more than 600 posts per day, almost 2,000 registrations per day, and more than 230 online users every day. And we got requests from 6,600 different IP addresses all over the world, but they were mostly from the US and Eastern Europe. What was very interesting is that we noticed that on the forum, 1/3 of the IPs that were acting on the forum were actually registering at least one account, but never posting any message. And so that led us to think that there may be some kind of business related to selling forum accounts. Also because we noticed also the inverse, meaning that we noticed that some IPs that were posting to the forum and had valid credentials, but they never registered anything. So they probably bought accounts from somebody else. Finally, we also identified some malicious content on the forum, because we analyzed all the links that were posted in each forum thread, and about 1% of them led to malicious content at the time of analysis. We checked this by using Google Safe Browsing and WebOwet. We also did some simple message categorization on the forum, just using keyword-based matching. And this allowed to identify some spam campaigns. From what we see in the graph, we saw that the most trendy topic is related to drugs, so pharmaceutical ads. And then we also have SEO and electronics and so on. Another interesting analysis we did was on the normalization of the time of attack with the location, with the geolocation of the IP that was attacking. And we can see it especially for post-exploitation sessions that are manually typically that are manual. It's the blue line. And this shows that, as you can see, attackers typically sleep at night. So especially between 4 and 9 a.m., we have a very low percentage of attacks, while during daylight hours, day hours, like in the afternoon especially, and afternoon, evening, they're very active. This trend can be seen also on the exploitation sessions, but it's less clear because, of course, exploitation sessions can be run also on automated systems, and these can run at night. Okay, let's go to the final phase of the attack analysis, the exploitation sessions, the post-exploitation, sorry. In this phase, we analyzed a total of more than 8,500 interactive sessions that were run on known and unknown web shells. So the known ones were the shells that we had made available to attackers on our honeypots, and the unknown ones were the new ones they uploaded. As I said, the average session duration was 5.5 minutes. We also collected some sessions that were lasting more than 1 hour, surprisingly. And we built a small parser for parsing the commands that were issued to the web shells from the logs, from having a look at the web server logs, and we found out that 61% of the sessions uploaded at least one file to the system, and 50% of them tried to modify existing files on the system, or actually succeeding in doing so. And in 13% of the cases, the file modification led to an actual defacement of the website. So all this analysis led us to the final goal of our study. That was the analysis of the attacker's goals. So by doing file normalization and similarity-based clustering on the files we collected, we were able to build clusters of behaviors. We manually labeled these clusters, and we found out that in 37% of the cases, attackers attack websites to perform a second stage of the attack, so to perform a manual attack. In 28% of the cases, we have defacements. This is typical, especially for script kiddies. We have in 7% of the cases, for example, the upload of phishing kits or spam-related stuff. We also have denial of service or brute forcing scripts, drive-by downloads, and so on. So just to give you some more details about the file analysis, and this relates more to the second phase of our study, the newer one. So to analyze our files, we have to first clean up what we get. Because especially for files that are uploaded to honeypots, they're quite dirty, they contain syntax errors, or they're sometimes broken. So first we do some stripping on the file, depending on the file type. For example, we remove comments. If it's source code, we remove comments, we remove extra white spaces, we remove email addresses from some especially web shells that are typically personalized by the attacker by inserting his email address. And then we do, if the file is a PHP file, we also do a dynamic code evaluation, because most of the PHP files we collect are obfuscated. So we run a dynamic code evaluation using eval-hook, that is a PHP extension for hooking into the eval function. We run the file until it gets deobfuscated. And this allows us to deobfuscate actually most of the PHP files we get. And then once the files are cleaned, we perform a similarity clustering. Well, what is this? It's just a way to identify typically code reuse or code development. So we want to see if there are web shells that are typically used by attackers, and if they actually modify the source code to personalize them, or if they they just steal code from other people. How to do this clustering? There are several approaches. We can use plagiarism detection algorithms, but these algorithms are precise but really slow. We cannot use them for large data sets. So we ended up choosing a couple of tools that are taken from the forensic world. There are SSDeep and SDHash. You may know them. These are called piecewise hashing tools, or fuzzy hashing. They generate a fuzzy hash, and they compare fuzzy hashes. And so basically, if you give them two files, they're able to tell you how much these two files are similar to each other. And these tools are fast and suitable for any kind of file, also binary files. That's very interesting. So by using these tools, we're able to build our similarity graphs for the files we collected. This is an example on the web shells we collected. And we can see, for example, that we were able to find a lot of code reuse, especially with regard to some web shells. The ones we have already made available on our honeypots are the ones that are labeled. So you can see, for example, angel.php is a very common shell that is used by attackers, as there are many other variants that are very similar to that. Same is for C100 and upload shell.php. There are also some files that are not similar to any other. You can see that the small points that are alone in the middle of the graph, but these are very rare. So finally, to the end of our project, that is, well, to the last part of our project, it's about clustering new data. So we started our honeypots again this year, and of course, now we cannot manually label all data we collect. It's too much. We would need like 3-4 people full time on that. So we can use the old data as a starting point. What we do is we start with the labeled data set we labeled manually last year. And for every file we get, we receive on our honeypots. If the file is similar to a group that has been already categorized, we add the file to that cluster. Otherwise, we just create a new cluster and allow the analyst to manually define the cluster type for that file. Of course, it would be nice to provide a tool to help the analyst in doing so, because it's a quite tedious task. So I'm going to show you the web interface we created. Hope the connection is still alive. Looks not. So this website has been created by mostly one of our interns. Let's check. No. Sorry. It's the Disney wireless network. How long do I have? Like 5 minutes? 10? 15? Okay. Doesn't connect, huh? Well, I'll try. Okay, so I have time. Okay, I have time. We can wait for the wireless network to associate. Maybe. So what I'll do in the meantime is I'll skip to the next slides and wait for that to tell me he's connected. Okay, just some examples of attacks we collected on our honeypots. This is an example of a drive-by download we received on the 28th of February last year. It was a file that was called into.html that was uploaded to one of the honeypots. It contains a obfuscated JavaScript, as you can see. Just before going there, trying to decode it and wasting time, we just submitted it to WebOet. And WebOet had actually already seen the same attack on the same day we collected it. And the file was actually loading a remote document that was launching two exploits. As you can see, it was detected as malicious and launching two exploits against those two CVEs. Another interesting attack we collected was a tentative of a privilege escalation against one of the honeypots we had. It was submitted on 9 of February 2012 by an Hungarian IP that uploaded a file called mempodipper.c. We checked what it was. It was a known exploit for CV 2012-56. And that was interesting because it was a very recent exploit. At the time we collected it, it had just been published 2 weeks before the day of the day of the attack. So it was a quite known, quite new attack. What the attacker did, he was trying first to compile the code by using a web shell. So he logged into the web shell and tried to run GCC. But sadly for him, there was no GCC on our honeypots. So he was smart enough. So he said, okay, I'll try to upload a precompiled binary. He compiled itself. He uploaded the ELF file to the honeypot, but then luckily for us, the kernel of our VMs was not vulnerable. This is another interesting example of defacement. So as you may know, defacements are very lame. I would expect them to be run by like script kiddies or people who really don't have anything better to do during the day. But in this case, in March 2012, we received this defacement by a German IP and modified a page on the static website using one of the web shells we made available. He inserted this page. And we had a look. He actually put a link to his Twitter profile. We had a look at the Twitter profile of the guy, and we were quite surprised in seeing that the guy had more than 400 followers and more than 1,000 tweets. And he was actually advertising this another link on his Twitter profile that was linking to Zone H. So if you don't know what Zone H is, well, it's a website that is used by criminals, script kiddies, call them however how you like. But it's a website that is used to showcase attacks against websites. So if you hack a website, you can go to Zone H and submit the URL of the website you attacked. And Zone H will happily just take your URL, take a snapshot of the homepage of the website you defaced, and put it in his database. So what we were able to see by just visiting the Zone H link the guy put on his Twitter profile was that the snapshot was actually taken last week. That as of last week, the guy had 42,000 defaced websites. There was a massive number of websites. So I wonder why these people do so. Well, you can imagine. You can imagine the time you need to manually deface 42,000 websites. So I guess the guy has really nothing to do in his life, or maybe you guys know, maybe there are ways to monetize defacement. Well, if you know what can be the purpose of people for doing so, just let me know. I would be interested. So let's see if the Wi-Fi network is working. So, come on. Ooh, okay, cool. So just be patient. Time to connect to the work VPN. Okay. Okay, finally. So this is the website, the beta of the website we developed. So if you go to the home page, you're gonna see the result of the analysis of the files that were received by our honeypots yesterday. We see, for example, there were like 6% attacked scripts, 73% of the uploaded files were web shells. We had some mailers, we had some brute forcers, we had some defacement pages. These are unique files. So, of course, the number of actual files that were uploaded is higher than what you see. We can go and see graphs of the files we collected, if it works. Come on. Seems the connection is down again. Oh, oh, come on. I'm sorry. It looks not to be very reliable. Hope I don't have to do like this for every page. Okay. Okay. This is the graph page. You can select the date. For example, we want to see the graph of clustered files for, let's say, last Tuesday. He's creating the graph. And what we see is this nice JavaScript graph here. You can see there are many clusters. The size of each node is the number is related to the number of files of times we have seen that file. So we can see, for example, this is a c99.php. You can click on that, and it's going to tell us it's c99. It's a type web shell. It has been seen in clusters that are a web shell. It's probably a web shell. It has been seen 6 times. First time it has been seen, it's 14th of June, and the last time it's the 17th of June. We can open it. Okay, and this is as you can see, it's an obfuscated PHP files. So how did it find out it was a web shell? Then it's because, as I said, we normalized the file, we ran the decoding, and it looked like a web shell. As I told you, we can offer, we get new files, we don't know what they are, we can actually clusterize them if we want. This is for the analyst. So it says there are so many clusters to label. Okay. There are so many files to label. You have to go manually through them, and you can select their category. So for example, I don't know, we can check this cluster. It contains 7 files. I hope you see, can you see this? Maybe it's better like this. Okay, these are 7 files in this cluster. They're all similar to each other. Let's open lol.php. What is this? Okay, it's another obfuscated shell. But there's a comment that actually says r75.gen.tr. That is, I think that's a website distributing web shells. So that's probably a web shell. So if we are sure about the fact that this file is a web shell, we can actually say, okay, this file is a web shell. And we have selected the category. and it doesn't, okay, it doesn't fit in the screen. I can't go down. Crap. Whatever. Then you can select the category, and the cluster will be categorized as a web shell. Once we have categorized files, we can go to clusters if we want to analyze what we already collected and what we already categorized. So, for example, we can go and check what we have in the phishing category. It will show us the clusters we have that contain files that are phishing packs or phishing files. Let's go to this cluster that contains 9 files. We can open, I don't know, united.html. It says it's a phishing pack. We can open it. Okay, this time finally we have something in clear. It says Santander e-banking. That's a Spanish bank, I guess. And then, well, if you actually look at the HTML, it's a web page that says, basically, insert your personal information, and I don't know, you can log into your account and so on. The typical phishing page. Perfect. Yeah. For example, we can have a look at, let's say, brute forcer scripts. This is a quite common category. Let's check cpanel.php, if that works. Doesn't work? Okay. Let's go to botnet. So maybe the connection went down again. Well, it's not a big deal. Just to show you an example. Yeah, the connection went down again. Well, it's not a problem. You just saw you saw how it works. I can go back to the conclusions. So, as I showed you, you may not be surprised by some of the conclusions, some of the things we found. Of course, for example, we found that there's a strong presence of Eastern European countries in spamming activities on the forum, especially. We found out, for example, that scam and phishing campaigns are often run from African countries, and Nigeria in particular. That may not be surprising. We also found out, as I showed you, that pharmaceutical ads is one of the most common spamming topics. Okay, that's fine. I guess you all know that. But we also had some unexpected results. Sorry. We noticed, first of all, that most of the attacks nowadays still involve manual activity. That was quite shocking for me. We also found that many IRC botnets are still around. I just wanted to show you a botnet in the last example, but I wasn't able to do so. But still, there are many IRC botnets around. And this means that despite the fact that these attacks are have a very low sophistication nowadays, so you see around the Flame, Red October, and so on, but this means that these attacks are the most frequent ones still nowadays, and they represent a large fraction of the attacks to which vulnerable websites are exposed every day on the internet today. So if you have a personal website that is vulnerable, you're very likely to see one of these attacks and not one of the targeted special attacks, super sophisticated ones that big companies see. Okay, that was all. I would like to thank especially the master students that were helping me with the log analysis, especially Marco and Roberto, and for the file analysis phase and the website, Maurizio, who was actually going to start a PhD this year. And thank you for listening, and you can actually ask me questions both in English and in French if you want. Thanks.
Thank you very much, David, for this interesting topic. Beyond all this way to do attacks on the web, David also enlightened us about the strategy, how attacks can spread on a large scale. Thank you very much for this. Do we have any questions? Yes, I'm coming.
Okay, hi. I have one remark and one question. you're okay with that.
Yeah, can you just go
yeah,
closer?
sure.
Yeah, thanks.
First of all, I don't agree with you when you say that Zone H is a criminal website. I think it's more like Shodan HQ actually, but with screenshots. And from an attacker perspective, it allows us, security analysts, hackers, wherever, to see, you know, real things, because people in the industry tend to hide when websites are hacked, tend to say it's infamy, it's lies.
Okay.
So,
Yeah, thanks for this. Yeah, I completely agree with you. I mean, it's not, maybe I said criminal, I want to say, I mean, it's for people who want to showcase what their attacks.
yeah.
People who, maybe some of them want to brag about what they do, they want, yeah.
Because sometimes it's not even, you know, attackers who screenshots them. Sometimes it's just like random people on the internet.
Sorry, it's about?
Sometimes it's just random people on the internet who see the attacker and just
right.
label it.
I see your point.
I can
Yeah.
screenshot
Yeah,
it
yeah,
and
yeah.
say, guys, yeah.
You're right.
And okay, the question: the websites you were running, what was it? You know, because was it just random websites? Because now we get so many motivational whatever attacks. You know, like Anonymous of Israel, where they're attacking only Israeli and Jew related websites.
Yeah, so as I said, so our goal was to study the typical attack against the typical website. The aim of our study was not to go and try to fetch those targeted attacks or attacks that are targeted to big companies. So our goal was to study the typical attack. So what we installed was actually these web applications that are the most common ones. They have known vulnerabilities. So we had a typical WordPress, a Simple Machines Forum, OS Commerce, Joomla. So yeah, we're not dealing with high targets, high-profile targets. It's really about the study of the mass.
Any other question? Ce sera la dernière question. En anglais ou en français?
Hi. You said that most hackers went to your website through search engines. What are the queries that they use? Are there general queries about the topics on your website, or more queries targeting internals of the PHP or whatever that runs your website? And more generally, how can these studies help detect these attacks?
So you mean how can we detect a potential attacker from a query? Or
yeah, from a query or whatever, from their behavior, maybe.
Yeah. Okay, so that's an interesting question. So we had a look at as I said, at the referrer with which the attackers reach our websites. As I said, most of them come from Google. The analysis of the dorks that were used showed us that most of the attackers reach the actual our website because their website runs a certain web application. So attackers were looking for like WordPress or strings. They were searching for strings like powered by Joomla and so on. So that was the most typical way for an attacker to reach our websites. However, there are some attackers that reach the websites, for example, the one hosting the web shells, by looking for a web shell. And in that case, the way they search for a web shell is not by searching c99.php or web shell, but they typically use the content of a web shell. I may have a screenshot like this. So this is a web shell. As you can see, they don't search for C99 shell because that is very easy to change by an attacker. The attackers typically personalize their web shell, so they change the title and so on. So they usually look for the title of subsections. Like they insert huge strings, and they write, for example, in Google they write encoder, tools, proc, FTP brute, sec, SQL, PHP code, update, feedback, self-remove, logout. They write all of this So they're sure to receive results that contain all of these words that are typical for web shells, actually.
Okay, thank you very much for this interesting talk. I think we can applaud him once more.